we'll get rolling again. So this presentation was designed to help you understand what the CSA A440.4 design standard is. So that's a standard that's put together by a committee, and they look at what are the problems that we experience in Canada, where those problems are, and what do we need to do to fix them. So really, it's the best practice and code requirements for durable wood frame construction. So here's what we're going to talk about today. We're going to talk about best practice, first, second plane of protection, how we integrate CSA into the code, and then Mark is going to talk a little bit more at the bottom. We're going to talk a little bit about the ASTM testing, but Mark will talk about that more in the next presentation. So that'll give us kind of an overview of what we're going to talk about today. Now, one of the things we strongly recommend is if you haven't seen the LEEP program on exterior wall installations, one of the challenges is when you're trying to integrate a window with putting exterior insulation on, how do you get that integration to work together? So the two programs that work really good is the LEEP exterior wall insulation program, because that talks about first, second plane of protection, how to get the insulation in the right location. Does the weather barrier go outside, inside? How does it tie into the window, and all those details? So that's one I'll leave you with. Now, the reference materials will be provided at the build booth here after lunch. So we've got a really nice handout with a lot of those materials. And at the end of the discussion today, I'll put a QR code up. CSA A440 has actually published online video and visuals on how to install windows that meet CSA 440 without having to actually buy the standard. So I'll put that up at the end of the presentation here. All right, so some of the key components of the CSA 440 are the fact that it is dealing with window installation for residential buildings and for retrofits, and it's focused on wood frame construction. We talk about shimming and anchoring. Now, we don't see a lot of anchoring and shimming with regard to vinyl flanged windows, but if you're putting box windows in, those are critical details that need to be done. Subsill flashing is a very important one, so we're going to talk about that. Air and water leakage testing. So how do you know that the window is going to perform properly once it's installed to the wall? You know, what are the mock-ups and the testing that you can do to verify that? And then the installation requirements to meet the code and the standard. Now, a lot of people refer to CSA 440, but they don't think about that dot after the 440. And actually, there's a whole bunch of standards now that CSA has produced. So if you're looking for information on energy performance of windows, you're going to look for 440.2. Then there's a selection guide, which is 440.1. You have a user guide for energy performance. The one we're focused on is 0.4. And coming with the next revision is going to be a 0.5, a user guide for the installation. And that's already been developed. It just missed the 25 code, so it'll come out in the 2030 code. So just a bit of an overview of CSA standards. All right. One of the things about the CSA standards that people don't often think about is that standard changes just like the building code changes. So in 2007, you might recall you had a little graph there called a nomograph, and you would figure out what the exposure was, what the overhang was, how much wind and rain was hitting it, and that dictated whether you had to put some kind of protection on the sill. So 2007 was related to earlier codes. 2019 is the current CSA standard 440.4 that we're using right now, which is in the 2023 National Building Code Alberta edition. Unfortunately, the 2024 did not make it into the 25 edition, so we're stuck with 2019 for the next edition of the code. So for the next 6 years, we're going to be stuck with 2019, which is probably one of the worst standards that we've had. Now, having said that, looking at the way the standard is written, the concepts are really good, but it doesn't have any mandatory sill pan protection. which is one of the big negatives of the 2019 version of CSA 440. So to understand why that's important, if we look at this drawing here, and you look at an old building, right, what do we look at in terms of performance on an older house? Well, when you didn't have much insulation in the wall, or you had horsehair in there, or you had, whatever they put inside the wall, there wasn't much insulation. So there was lots of heat loss through the wall. Now, if there's lots of heat loss through the wall, then you're not going to get condensation on the exterior of the components, right? On the exterior siding, exterior sheathing. Not only that, but we didn't have a lot of vapor barriers and we didn't have a lot of air barriers. So now the air can pass through that very quickly too. So if there's lots of heat loss and lots of air leakage through there, what happens to the moisture? It gets dried out really quickly. So you take an old building apart, built in 1950, 1960, you pull it apart, looks like it was built yesterday, right? Because the heat loss absorbs the moisture, and then the wind blowing through will get rid of it and dry it out. So do we have a microphone? We got a question here.
Yeah, thanks, Darrell. It's always in my understanding a huge part of that was mechanical systems too. Mechanical systems drew combustion air out of the building. Everything had a chimney, like your neutral pressure planes at the ceiling.
That's another one, right? In the old days, you had a furnace with a B vent. So as the air got sucked through, the air outside was drier, it came in, it warmed up, it absorbed all the moisture. So you have all these things going against you now with a modern constructed house. In the old days, we had a fireplace as our heat source, right? And that created a big negative draft, pulled air in through the walls. So those are things that really changed in our modern houses. The other thing that really changed is what kind of lumber was used in 1920, 1930, 1950. We had fir. You ever renovate a house and pull the fir out of it? You ever try to drive a nail back into it? You got to pre-drill it to get to nail it. It's just like rock. And old growth fir versus new growth fir. When I started framing in 1978, we always had old growth fir, right? You would only see a knot every 10 boards that was just straight grain in the wood. And very resistant to moisture. So fir lumber, super resistant to deterioration of moisture. Now we're using, 10 to 12-year-old trees to produce 2x4s and 2x6s. So very different in terms of what the material can handle. If you look at the wood itself, in the window was made of fir as well. So, look at the slope on the bottom sill here. Do you think these guys understood water when they built those windows? See that little notch in the bottom of the window? What was that for? Little curve cut, right? So you didn't get the capillary suction underneath that whole window right to the inside. You got a back dam on here, right? You've got an opening here, so whatever moisture is in here, it's pretty much going to let the air blow through and dry it all out. Why didn't windows deteriorate? Because there was nothing holding the moisture in there. So when we look historically at these, right, we had moisture-resistant materials, we had air drying, we had slopes, we had deflection because we had these big overhangs. We didn't have any metal. Anybody been to Nova Scotia? You go to Nova Scotia, walk around and have a look at the houses. They're built in 1680, 1750. There's no metal flashings on those windows. And those windows are like 300 years old. So if you look at the way they were designed to deflect the water and keep it away from the wall. So that's, things like surface tension, breaks, kerf cuts. They dealt with water in a very different way. So what do we see today? If you drive around today and you look at window installations, is this common? What's it cost you for peel and stick these days? 75 cents a foot? Any difference between this and a house wrap right now? Right? Exactly the same. You spent all that money on it. You didn't take a roller. All the materials today are pressure sensitive. If you don't have a roller in your truck for putting peel and stick on, don't waste your money on peel and stick. Or, you look at this one. They've got caulking and peel and stick, but the peel and stick isn't even embedded into any of the materials. Or how about this one, where the flange, which is where the water's going to track down, is behind the flashing. right? So we're not thinking this through clearly. In the old days, these things worked because the water would drip in, but the wind and the air and the heat loss would allow it to dry out. That doesn't work anymore with high-performance walls and high-performance windows. So we have to understand the process of how a building goes together. Mark.
Thanks. Could you go back one slide?
Yep.
I love the picture on the right because that shows how much the designer matters as well. You can't design a window in that location and then just fault the trades when it doesn't go well. Right? You got to set the trades up on site for success. And that comes with leaving enough room around these openings to properly detail and work. That's just a detail that's not going to go well. It's a design concern as much as it's a materials and install concern, even more so perhaps.
Yeah.
So don't let your designers think they can't come to these sessions. They got to come too.
Well, and just to touch on that a little bit more, how many details do we put in a residential blueprint? As few as possible. I hear builders go, I don't want to put the details on there because then I'm responsible. News alert, you're responsible anyway, right? If that leaks, that's your fault. Not the trade who did it, that's your fault. So we need more details, more information on why we need to do things a certain way. So one of the things we need to understand is the building code talks in first and second plane of protection. Right? So siding's first plane of protection, windows are first plane of protection. With the water hitting the building is deflected away from that first plane of protection, but some gets through. And when it gets through, we have a second plane of protection to take that water, and the second plane is your weather barrier and your flashings, and it takes that water, it runs down, directs it out, kicks it back outside. So if that principle is in play, it performs really, really good. So understanding first and second plane of protection. Your first plane is your cladding and your sealants, the caulking around the window, right, that prevents water entry, but then not caulking the window behind to let water that gets in there to drain out. Now, when you look at the second plane of protection, that's the membrane that goes around the window. That's the sill pan. That's the window weather barrier that folds in at the sides. And then the flashing at the head is part of the second plane of protection. Because as the water runs down the wall on that second plane of protection, we lap that over top of the flashing, that second plane of protection, and we kick the water back outside. So that all works together. Now, I referenced here PCF 1950, 1951. If you did any look at the new code changes for 2025, there's a code change requiring the second plane of protection to be in place, and for this membrane at the bottom to be an impermeable sill protection. So there is a code change coming out in 2025 that's going to require that, even though CSA A440 currently only requires it for doors and mold windows. So this is the CSA standard. The code change coming in 25 is going to require protection on that rough opening, that second plane of protection. So when we look at a window like this, right, second plane of protection, backup system, collects the water, drains it back outside. First plane of protection, deflects the water, reduces the amount that gets in there. We have to look at these three principles here. And this is the Joe Steebrook principles that we learn about. So control the moisture entry. Not stop it, just control it. Reduce the amount that gets in there in the first place. Control the moisture accumulation. We don't want water getting in there and building up. So how do we reduce the accumulation? Well, we either let it drain out or we dry it out, which is our removal aspect. Right? So these all work together as a system. So when we're dealing with removing the moisture, the drainage and the drying are the two big ones. So if our system can't control the moisture entry, can't control the accumulation, that third one becomes really critical. So you put a window into an opening, what's the first thing most people want to do? Seal the window four sides. Will water get into the rough opening? Absolutely. How do you perform drainage or drying if water gets into the rough opening? because the rough opening is part of the system. So that's what we're going to talk about in the balance of this discussion today. So always treat our fenestrations, or windows and doors, as if they're porous. Just assume there's always going to be a point in time where water gets into the rough opening, so we need to drain it and dry it out. We have a classic example of that on every vehicle. How come we don't seal the outside of a car door or a trunk? How come we leave that open? And how come we put the weather stripping so far into the assembly? It's because we're relying on air to protect that opening. So you're driving down the highway, you have a very, very high wind pressure and it's pouring rain out. How much water is pouring through into your car? Nothing. But how much water is actually hitting the weather stripping? Probably just a tiny little bit. So there's an example of first and second plane of protection. The air that goes into that cavity pressurizes the cavity. So if it's the same pressure in the cavity as it is on the outside, what's causing the water to enter that joint? Nothing. It's not going to go in there. And if a little bit goes in there, there's no pressure difference. So all it does is go in there and fall down by gravity and drop out the bottom. So if we installed windows this way, would they perform better or worse? This is the way we look at windows and say, how do we stop them from leaking? We put the second plane of protection farther in where it's not in contact with the water, and we make that second plane more airtight so that we can equalize that air pressure so there's no suction of water coming in. Think about a window and how it's made. Did you know that the windows have internal drainage? Because when the wind blows and pushes the glazing, it separates the glazing stops, it separates the sealants here sometimes, and water gets into that window between the glazing stop and the glass. And if water gets in there and you get enough of it in there, where's it go? So you want that water to be able to drain out. So if you pull a window apart and take the glazing out, you'll find little openings that lead all the way to the outside to weep out of the building. Or weep out of the window, I should say. So those compartments take that water that gets in there and drain it back outside. Why do they work? Because of the way they're designed. If the wind was to blow in this opening, how much wind could actually blow into the building? Very little. So it pressurizes the cavity so the water can drain out, but it doesn't allow wind to blow water back in. And if it does blow in, it loses momentum. So if the water even pushed up to this point, it would never make it up here to make it inside the building. So that principle is a sound principle that helps us to understand when we're dealing with the rough opening, take the same principles here and apply it to the rough opening. That means water that gets in, let it out. Water that gets in, let it dry. Let it be removed by evaporation. So you look at the planes of protection here, right? When it's raining, there's where the rain is hitting. That's your deflection. That's your first plane of protection. Now, in the window itself, if water is getting in here and the wind is blowing and moving it away so this seal opens up a little bit, whatever water gets into this opening, we're draining that out through the weep in the window because we know water's going to get in there. So that same principle applies that if the water gets into the rough opening, we need a good airtight seal here, a back dam or a slope seal, or something to stop the water from going through, but more importantly, something to stop the wind and the air that's out here from passing through and coming into the building. Because if the air can pass through, it can easily carry the water back in. So it's all about stopping the air leakage. This is exactly the same principle as that car door we looked at, right? There's the inside of the car door seal. There's the flange. Why do you need to seal the flange? You don't really if you have everything else done correctly. And if you give the water a place to go, it'll go there. And then because there's no air pressure difference, gravity will simply pull it back out and it'll dry that space. So you notice where that joint is, right? It's on the window itself. Now, how do we get windows in Alberta? They come with the jam extension already on. How are you going to put that seal in there? There's no way. So as long as the jam extension is sealed to the window, you can take this seal and you can put it out here. And it's still going to perform just as good. It's all about that air barrier and that principle of first and second plane of protection. So here's your air barrier line, your pressure plane line. So it's going to come down. Sorry. Go ahead, Wesley.
What do you think about insulating that gap, Darrell, at the sill, in the sill pan?
Let's go back one slide. This gap right here.
That's right.
So PCF 1951 says, don't insulate the sill. So this goes back, way back to about 2013. NRC did a study and said, what happens if we insulate that? And what they found was that it blocked the drainage of the insulation. So what's the best insulator in the world?
Air.
Air. So what's the insulation value of this cavity in a window? Right? You think of that cavity in a window, you have a cavity here, a cavity here, a cavity here, a cavity here. Those all have insulation values because they're not letting air mix with the other area. So if this is compartmentalized, right, there's very little air blowing in there. So you are getting a reasonably good insulation value. In fact, that NRC study that they produced, it measured the temperature right here at the sash, and they found that a vinyl window, fully insulated, at minus 30 degrees outside, versus a vinyl window with zero insulation at minus 30 degrees outside. Take a wild guess what the temperature difference of that inside surface was. 0.5 degrees C. What about the risk of condensation in that cavity? What causes condensation?
It should be an exterior air environment. If you've got your air barrier down, right?
Right, so what's the humidity level here versus out here? Pretend it's not raining, it's winter time, whatever time of year. So if it's dry, you know, let's say it's 40% humidity outside, it's probably going to be 40% in there. What causes condensation to occur? A temperature difference will, but what happens when the temperature goes up? What happens to the relative humidity?
Goes down.
Goes down. So if it's, you know, let's say it's minus 10 out here, what do you think the temperature right here is going to be? Warmer or colder? It's going to be warmer. So if it's 40% outside and it's warmer in that cavity, what happens to the temperature? Goes up. What's the risk of condensation? Just went way down. So the risk of condensation without insulating this is very, very low. What about the risk of condensation up here? There's where we're worried about. And again, if we're worried about condensation internally, what's the R value right here of this particular window? Probably about R2. It's the weakest point in the whole assembly, depending on the type of material you're putting in there. So the risk of condensation, again, is fairly low in that assembly if you look at the building science behind what happens and why you would get condensation. So if the house is at 35% humidity, over here it's probably 80, 90% humidity. It's probably still not enough to cause condensation, depending on the temperature.
The other thing really is if we do get a bit of condensation in here, and this is a sealed sill with a back dam that's impermeable to water and drains to the outside, do we care, right? So it's really a low concern there, unless you put something in there that becomes food for mold, like the wrong kind of insulation.
Right.
But this is really, I love this slide for a couple of reasons. Number one, pointing out that this bottom flange is a location for the release of water is really sometimes, it comes up against well-meaning junior tradespeople that get told, you go seal the windows, here's a roll of tape. And how many sides do they think they should seal? All of them, right? You seal across that, and all this great work you've done, now you've got a holding tank for water instead of a way to let it out, right? So you got to monitor that sort of thing. The other thing is with the insulation question, I love this. in Ontario, at least, I wonder what practices here, but in Ontario, standard practices, install the windows, can of spray foam, 4 sides. We don't see back dams and we don't see sloped sills. So this is going to be an adjustment that people are going to have to make to their execution and to their thinking to understand what is the role of that spray foam and how is water going to navigate that detail if you don't make a change. So I don't know if that's common for builders here in Alberta as well, but that's something they're going to have to look
Pretty
at.
common. Yeah. I think across the country, anything that I've looked at, that's the most common is spray foam around the perimeter. And it doesn't mean you can't insulate that bottom cavity. It just means be smart about the insulation you use. Like if you put a chunk of mineral wool in there, extremely drainable material.
And what about, a high density insulation material as your back dam?
Yep.
What if you insulate from here this way? Are we causing problems with that insulation? There's other opportunities. So you just have to be more intentional about how you execute that detail, right?
Yep.
Yeah.
Yeah. You could just take a piece of styrofoam and use that as your back dam, as long as you bring your membrane up and over it. Because the window is going to compress that and hold that in place. So you're not worried about whether it loses its adhesion to that styrofoam or not. So those are little things to think about. Now, let's go to the pressure plane, because here's an important one. So if we look at the pressure plane, we want the line of the pressure plane to not match the line of drainage. Why is that? Well, the line of drainage is where the water is. And if we have a pressure plane, in other words, we have a high pressure outside because of the wind and a low pressure inside, that means that any break in this green dotted line creates suction into the building. And if we have water in contact with a hole and we have a suction, what does it take for water to go through an opening? I always use the mop principle, right? Moisture, opening, and a pressure. So if we can eliminate the opening, great. Or good luck, right? But if we can stop the air pressure, great or good luck. But if we can keep those two separate, like we know that air barrier is never going to be 100%. Anybody done a blower door test and got 0 air leakage? Right? Even a passive house at 0.6, that's 300 CFM on an average size house. That's still a lot of leakage. So you'll never get it airtight. You'll never get it perfectly sealed. So rely on stopping the water from touching the pressure plane. So doing that, right, there's nowhere here that the water is going to contact that's going to be allowed to suck in. So your membrane extends over that joint. The air barrier line comes in, is connected to the poly on the inside. This framing here becomes part of that airtight barrier. You can't blow air through a 2x4. So that becomes part of your airtight barrier. So that pressure plane or that pressure drop, as long as you keep that away from the water, you get very little risk of that sucking water in. Remember, we're controlling entry, we're not stopping it. Anybody spilled water on their shirt and by the end of the day they had mold growing on it? Right? Yeah, I hope not. But I mean, you ever put something in your hockey bag and then 2 weeks later you went and look in it and it's, yeah, right? So same principle. Let the water that gets in there, let it get out. So here's another example. Have you ever taken a water bottle and tried to blow air into it? Isn't there a giant hole at the end of it? How much air can you blow in there? And yet, if you cut some holes at the back side of this, the air would blow through here all day long. And if you had water shedding over this surface, that water would be getting into the bottle. That's your wall assembly. So when you look at the flange, if this is the flange here, and this is the interior air barrier, as long as you get a reasonably good air barrier, you're not going to be allowed to suck air through that assembly. It's just not going to work. So that's why these principles, and looking at this rough opening as if that rough opening was this bottle, you have a hole or an opening here for drainage, but you've got a really good air seal here. So in the CSA A440 standard, we're looking at air sealing, whether it's at the back of the window, depending on when you put the jam extension on, whether it's the back of the window or you're getting a good air seal here and a good air seal here. Maybe you're setting a bead of caulking here on top of the back dam before you set the window in. Either way. You're stopping the amount of airflow through, and the water is not in contact with that green line, with that air barrier.
Because it's so near and dear to my heart, I got to jump in because I love this slide for this example. I can't stress enough that in all situations, air leakage through our assemblies introduces more water than it carries away. Right? So all of the drying and draining that we're talking about here is not contingent on air moving from the inside to the outside to dry out an assembly. That will always hurt your assembly more than it helps it. So air tightness of the assembly and openings for drainage are different things. And I just have to highlight that, right? We don't have concerns. We understand now that houses don't need to breathe. Houses need to be as airtight as they possibly can to prevent moisture from getting into the assemblies that we're insulating. And then we have to control water by allowing proper drainage planes and openings from the exterior, keeping in mind where those planes of protection fall.
Yeah, that's a really good way to illustrate it.
In this model, the dam's further back, not at the jam extension.
Right.
Is there, because most times the seal on the jam extension is like a piece of tape.
Yep.
Are you worried long-term with that just failing and being wide open then?
Well, I am, but it depends on the tape you're using, right? What's the compression?
What just comes from the manufacturer?
I know.
It's like a thin piece of crap.
Yeah. That's one way to look at it. But some of those materials that they use, that butyl tape that they use, some of it bites into that PVC pretty good. So it really comes down to the compatibility. Like if it came with tuck tape on it, I'd be worried.
Yes.
Right?
Is there a optimal place for that dam? Like, is it better underneath that, or does it, maybe it's not?
Well, the problem is if you get the jam extension shipped with the window, how do you possibly get in there to seal that? So one of the things I always recommend is when your windows come, check that tape around there. And just take a roller and just give it an extra little push if you want. For the most part, it works really, really good. But every once in a while, it's going to fail. But even if it fails, let's say this failed. Let's say the tape let air blow in and out of this location. If you've got a good air seal here, this has got air blowing in. So the air comes in here, it's raining, it blows, it brings rain in here. Very unlikely it's going to be able to pull it up here. So now the rain's in this rough opening, but you've got a back dam, and it's just going to drain back out.
I just was more wondering if it would change the R value at the point on the inside, because if air was flowing through that jam extension, would your R value drop?
Absolutely. That's the danger.
Then also you have,
So you have the potential of having condensation in here.
which can still flow.
Yeah. So, all right. Excellent point. That's why you do pre-drywall. Air tightness tests. That's why we recommend those. All right, here's a really busy slide, but this is the concept, right? If you take your air barrier and you follow it all the way around and you look at where the water is, the green is air barrier, the red is water, and you look at, positive and negative pressures, there's very few areas where they're both in contact with each other. In other words, the water's going to get into the rough opening, the water's going to get into the window. If the window fails somehow and water gets in here, you've addressed that. We did a house in 2011. We went there and the windows had failed. And the window manufacturer said, yeah, our bad, it's our fault. We'll fix the windows. What about the $100,000 damage on the back of the house? Right? We had to strip the whole back of the house. It's a big custom house, $2 million house. Well, that's not our fault. You guys should have put Silpan in. Right? So, same principle. Treat these windows as if they're porous. Give the water a place to go and a place to drain out. Go ahead, Mark.
That just reminded me of one of my other favorite sayings that we hear in this industry. There are two types of windows. There are windows that leak and windows that will leak. And that's treating them as porous, right? And even in the case where the window unit itself fails, where are we really concerned about leaks happening? Mostly, it's the installation that's the weak point, not the window product itself. Yes, it happens. Yes, you get failed seals and there are things like that. But as Darrell's shown with the design, these windows are designed to self-evacuate in the event of minor failure or of some water penetration. So really, window leaks, when we talk about them in the industry, 99.9% of the time have to do with the installation of the window, not the window product itself. Window suppliers, manufacturers really like it when I say that, because it gets them off the hook a little bit. He's buying coffee after this. But no, but that's the point. And if you think about a slide like this, really, from this point up, all of those little red arrows, that's the domain of the window manufacturer to get that right. The window install is worried about everything from this point down. That's what you have control over. And that's where we have to focus on understanding that sill and that back dam condition.
Yeah, exactly. And think about a window installation. You put a giant PVC window in. What's the structural ability of a PVC window, right? And you got setting blocks in there somewhere, setting blocks supporting the glazing, which transfers it to the PVC. So you have a setting block here, setting block here. The framer puts the block for support here between the two. And that 600-pound window over the next 5 years starts to sag. The seals break, water gets in there. Whose fault is that? You ever had a framer come back and say, oh, that's my fault, I'll warranty that, right? So things happen like that. So that's why treating a window as porous protects us so that long term we don't have that risk associated with what can happen.
Question, sir.
Yeah.
This is for the installation. I'm looking at there's a very little space between the nailing flange and the 2x6. How does the installation or builders maintain that? Most likely in the industry, the nailing fin is used to skewer the window with the rough opening. And at the bottom, if they screw it up, you don't have any room there. Plus, it's such a little space. It's very difficult to maintain that, sweet spot.
So I should have brought a piece of house wrap. I was down in Vegas last week for the builder show. And when they were doing, what do they call it? It's a house wrap, it's a drainage wrap material, right? Well, the new ones that they have are almost like a sputter coat on the surface. And I would argue up and down that has zero drainage because it's so smooth, it's so flat. It's got 94% drainage. Right? So it's not the size of the space. So if you think of a PVC window, it's never going to be perfectly flat to the wall. So there's always enough space there to let drain it. Because remember, we're talking tiny little amounts of moisture there. Right? We're just talking tiny little droplets of moisture. But if they build up, that's where the problem lies. And we know hydrostatic pressure, if you only had half an inch, what's the hydrostatic pressure for half an inch? 125 pascals. Pushing down on that window, it's going to push itself right out. So
the wall assembly that we rolled up here that's behind Darrell has the flange on the bottom. And so if you go and take a close look at that, you'll see the realities of installing the materials that go behind the flange itself, the frequency of the nailing. There may be points along that flange that are sealed, but there will be plenty of points that are not, that have a microscopic channel, that have the ability to release that water, exactly as Darrell was describing. And so as long as that's not taped over, we've found that you're going to be good, right? That's the key step, is to leave that open so that those microscopic drainage planes can do their job.
Yeah, and they don't have to be very big. Now, one of the things we always recommend, as a building envelope specialist, I always told guys, on the face here, take a couple of pan screws and put them on before you install the window. Or if you're putting the shims on, put the shims on and let them be proud by a 16th or an 1/8 of an inch. There's all sorts of ways you can increase that drainage. But conversely, you don't want as big a space because the amount going in is going to increase. So that's the principle there. So this is a window that doesn't have a jamb extension. It's going to be put on later. This is a window with a jamb extension. I'll just get this out of your way. So really it's the air barrier that we're looking at here between these two assemblies, right? One is much easier to do than the other. Now, one of the things to think about is when it comes to deflection is the size of the overhang. So, we did a lot of design work, or I worked on a lot of design work over the last 25 years. we'd have designs like this with zero overhangs. Do you see a potential failure here in this assembly? So the framers put the house wrap on, they put the windows in. What if the siding guy doesn't get correct overlap from here over this house wrap here? You got an entry point. What if up here, because this is a peel and stick, it's secured to here, so the siding guy goes, ah, the heck with it. He just brings his house wrap over top of that. And now everything gets directed in behind there, and everything's behind and into the rough opening, down in the wall. What are you doing with the water that's getting into that rough opening? So the potential is always there that you get water into the rough opening. Overhangs like this give you some protection, but there's no guarantee that the water doesn't get into the rough opening. But we know from studies that having an overhang reduces window issues by 25%. So larger overhangs, zero overhangs, big difference between the two. So deflection is a key component. And where it's a key component is looking here at the tie-in. So here we've got the house wrap going in behind the J trim on the soffits. Here is the old-fashioned way that when I was a site supervisor, this is what we did everywhere, right? The paper does not extend up and behind. So you get wind-driven rain hitting up here, draining down. If it finds a joint in the sheathing, it's behind inside the wall assembly. Or it just comes down and it runs around here, finds a joint in the floor, and now it leaks into the basement. And the amount of times we found this lets water into the second or the main floor windows. The upper windows are protected, but it hits the joint in the sheathing, it comes in the main floor windows, and you're going, everybody's doing water test on the window. Well, no, it's coming in from the soffits. And it's all the way down. So again, that sill protection protects you if the water gets in there. Same principle behind decks, right? If we don't have proper membranes at decks and the water gets behind, finds a joint in the sheathing, it's into the rough opening. So that's why sill protection and protection of that rough opening is so important. So when we look at that, we want to avoid filling these cavities with so much material that if water comes down, so here's your joint, water gets between the sheathing and it drips from there into the rough opening. If you fill this up with a non-drainable material, the risk is you build up hydrostatic pressure and then the water drips back into the building. And you'll get dripping at the jamb extension. You ever go in a house and you see these brown drips where the window and the jamb extension connect? That's the first sign that the water's coming from an upper source. So if you're looking at a window and it's leaking, and you walk in and you see these brown stains, which are resin from the OSB, you know that the water's coming from something above. It's not the window itself. So learning how to diagnose that is important. But here's just an example of, putting a little bit of a protection in, letting the water that gets in there drain back out, whether it's a door or a window. So some of the ways that we can achieve this are, you can put a piece of lumber behind it. This is a common one in Ontario where you put a little metal backstand, especially in commercial construction. That's a very common one. In Eastern Canada, they like to use clapboard because they use a lot of clapboard. So it's just a cedar piece of siding that they put on there and it's got the slope built into it. Or you can cut your bottom sill. This is a real pain in the butt, but if you want to do that one, you're welcome to do that. One that I've used in the past is make your rough opening 1.5 inches bigger, put a double bottom plate, and then just drive a wedge in it and you get a slope. But let me ask you a question. If you pour water on the table, how much water before it starts to run and run off the table? So even if you have a flat sill with a back dam, the water's not going anywhere. So what's wrong with a backer rod and a bit of caulking? There's your back dam. So you don't have to make it really complex to make it perform. Now, one of the things here, if you look at the WRB here, the weather barrier, a lot of times, if you just take the peel and stick and put it on here, it's just going to stick to the wood. How do you get your second plane of protection up and underneath it unless you pre-wrap the bottom of that so that the peel and stick is over top of that WRB? So you have to introduce that and make sure that's in place. So again, the back dam is designed to collect the water and drain it back out. The window itself is designed to collect the water that gets into the shim. All right. If you look at where the location is here, in a back down with a 1-inch foam on the exterior, the challenge here is the support for the glass. Right? How do you support the glass if you're putting exterior insulations on there? Because you have a setting block in here, you have a weight, you know, it could be 300-pound piece of glass in here. That needs to be transferred through the setting block, through the frame, and onto the support block underneath, and transferred down into the structure, not into the foam area. So when we're looking at these designs, the structural weight, like in this type of a window design, this isn't going to fly. Eventually, that's going to sag so much that you're going to lose integrity of the window and it's going to be damaged. So if you're putting exterior insulation in, you put a picture frame around the window. So the picture frame is designed to pick up some of the weight and transfer it back to the structural component of the building. Or you go into a window that transfers the load by moving the glass inboard, so it's sitting on top of the wall. Now, these windows are a little more expensive, but to me, that's well worth the expense. Because the glass is closer to the interior, you got lower risk of condensation, and the structure is supported properly on the structural components themselves.
Just a couple minutes.
Okay. All right. A couple of other things, just minor things. Structural shims should be water resistant, so that's important. Making sure the shims are actually in contact. This doesn't work, right? Because that's your structural support. So put the shims in, level that, and then that supports that window versus putting the window in and then jacking it up and trying to support it that way. So. Structural support for windows. We're not doing any box windows, but those are important as well. Like we have so many things to think about when it comes to window installations. Non-flanged windows. So we're not going to talk about non-flanged windows, so let's just skip past this. Installation basics. All right, so we'll just do a quick installation basics. Make sure that you don't have any material sticking up in the bottom of the window here. Make sure it's flush. Make sure it's level, square, and plumb. Those are pretty straightforward things that you need to do. Peel and sticks around windows. If appropriate, you might need a primer so that it sticks to the OSB. You're going to put that bottom bib in there. Then your self-adhered membrane goes in. Your corner tie, depending on you use a corner tie like this or whether you use a pre-manufactured one, they all work. Make sure that you use a roller to fasten that material. And then when you're looking at the material itself, the rough opening protection, you're making sure that that membrane, that house wrap is folded all the way in. And why would we do that? It really is dependent on what the insulation material that you're putting around that is. If it's got the ability to absorb water and it's wet, do you want that in contact with the wood? So that's what I use to dictate whether I'm going to put house wrap folded into the opening or not. And if you do, fold it all the way in so that you can make contact with the poly. Because if you leave it part way and then you come and do an air tightness test, where's the air leakage, on the inside or the outside of the house wrap? It's probably on both. And then your shims, making sure you get the appropriate shims. Windows installed, making sure you have the appropriate space up and down. Making sure the fastening is done right, right? What's the hole for in the window? Expansion and contraction. The window's going to move a ton. There's a 60-degree change in that window in the wintertime from when the sun hits it to when the sun goes down, if it's minus 30 outside. So that's primary reason. So these are all in the standard, in the CSA standard. Where to nail, avoid nailing in the corners, leave the bottom open for drainage. All right, so if you're going to put peel and stick, the drip, this protection here is typically on Alberta windows. So if you have a built-in drip, you don't need that. So we still see people putting that bottom flashing on, even though that they have a built-in drip. If you have no drip, then the code requires you to put this in. And this is part of first plane of protection. So it needs a bead of caulking on the face. All right. I'm not going to go through this one. Caulking is important. So here you have caulking. We're putting caulking on because that's part of first plane of protection, and it is a requirement in the building code. People forget that part of the building code. So, all right. I'm not going to get into the WRB, but suffice it to say, we need to provide drainage to get the water out. So again, this is getting into more of your wall assemblies, but rain screen details to let the water out. That same principle applies to windows. So the intersection of where you do the window to where the drainage occurs. So for instance, here you've got a rain screen mineral wool and you're recessing the window into the opening, but you've got the drainage plane, which performs really, really well. So in high performance walls, you can get into that kind of a detail where you're draining the water out. WRB location, yeah. We've condensed this quite a bit, so I'm just going to skip past here. Insulation around rough openings, poly air barrier, spray foam in the rough opening you can use. My preference is backer rod and sealant. And the real reason for that is because then I can dictate where the air seal is. I can maintain that drainage plane in the exterior perimeter. Here's what we don't want to see, right? Rough openings. Here's the connection between the glazing or the frame and the jamb extension. And without that tape that we talk about, here's what you end up seeing. So that's what we're trying to avoid. So backer rod, spray foam combination. Doors, by far, the most important thing is when you cut that bottom plate out, that better be straight and flush. Because how often does the framer cut the bottom plate out and then that little short little stub wall that's butted in on this side is not secured? And then he goes, oh, it's not secured. So he just nails it in without checking, and now you've got a wall that's out askew. And that creates all sorts of grief when it comes to installing doors. Technically, this is the requirement under CSA 440, is to shim the bottom of the door to allow drainage to occur underneath. No one is enforcing it, but that would be the detail that would meet CSA 440 right now. All right, I am going to wrap up here because Mark's going to talk about this specific aspect. So let's not me duplicate it.
Yeah, we're going to get a chance to look at this in real time now. So what's up on this slide is a visual diagram of an air and water pressure test that we have a video to show you. We actually took a window. I'll just get it playing. I think they'll walk you through it, but two different installation methodologies, the the 440.4 install method, and then an updated version for a better, good, better, best, a better install, and then put under this pressure test to see how they performed and where the water leaks. So I'll run the video, and then we'll have a few minutes after that to talk about what we saw in the video and to address any questions that come up from this presentation.
Okay.
Sound good?
Sounds good.